Hi boys and girls, Mr. Pancholi here. Welcome to the answers for your consolidation quiz from last week. So, pens and papers ready? Please have your quiz ready as well, your answers to your quiz. And let's go through your answers. We'll be making sure that you understood how we got to the answers and also correcting any mistakes that you've made. So, first question was about particle model. And it was about drawing and describing how particles in solids, liquids, and gases are arranged. And part 2 of that was how the movement of solid, liquids, and gases differs. You'll see here three boxes with the yellow dots representing the particles. In solids, we draw them in a nice, neat, regular pattern, all touching. You'll notice none of the circles are overlapping. In an exam, if you overlap the circles, you will lose marks because they're particles. Particles can't go into each other. So nice, neat, regular pattern. In a liquid, you'll notice that there are certain gaps, but they're still pretty much all touching. They're all very close together, but they're not in a nice, regular pattern. They're irregularly arranged. In a gas, they're not touching at all. They're all far apart. So, that's how you draw them. You describe them, like I said, in a solid, regular pattern, all touching, fixed position. In a liquid, irregular arrangement, mostly all touching. In a gas, they're all arranged far apart. Describe the motion or the movement. Well, in a solid, as you can see there is literally no space for them to move around. The only thing they can do when they get energy is to vibrate. Solid particles are always vibrating. When they gain energy, they vibrate faster. So solid particles vibrate on a fixed position. Liquid particles are able to move over each other. They can't just freely move around where they want. That's a common mistake. Liquid particles can only move over each other. In a gas, particles are free, so they move around randomly in random directions, and they move at random speeds. You can't really tell which particle is going to be fast, which particle is going to be slow. They all have their own random speeds. So random movements, random directions, random speeds. In a gas, in a liquid, they move over each other. In a solid, they vibrate on a fixed position. Please mark your quiz and correct any mistakes. Next topic was about density. And you need to know about the equation for density and then explain what density really means and how to find the density of different types of objects. So the equation for density is density equals mass divided by volume. We know that by the language we kind of use. We say that something's dense when it has lots of material in a certain amount of volume. So amount of material is mass, it's in kilograms, and volume is the amount of space in a 3D object, and it's in meters cubed. So density in kilograms per meter cubed equals mass divided by volume. In a dense material, if we compare a dense material to a not so dense material, the dense material has particles that are packed closer together. If they're closer together, that means that there are more particles in the same amount of space. So there's more mass per volume, density will be bigger. When we compress an object, for example a gas, because gas is the only one that you can compress, if you compress a gas, what you're doing is you're bringing the particles closer together. That means that in that same amount of volume, if you don't actually change the volume that you're measuring, but you're just putting more gas in, if you're compressing that gas, you've got more particles in the same volume. When you compress it, it becomes more dense. For a solid, regular shaped object, to find its density, we must know from the equation its mass and its volume. As with any object, for any of these particles, to find the mass, all you do is put the object on a set of scales and record the mass of it in grams or kilograms. To find the volume, that is what changes depending on the object. For a regular shaped object, you find the volume using a ruler and looking at the dimensions. If it's a cuboid, then it's height times width times length. If it's something like a cylinder, then it's pi r squared times the height, and so on and so on. To find the density, you must state this in the exam. You must write the last bit out. Find the density, you just divide the mass by the volume. For a solid irregular object, bear in mind, because it's irregular, we can't just get a ruler and measure its dimensions, because it'll have lots of different dimensions and sides and whatnot. So what we have to do is use the idea of a displacement can. Before we do that, we find the mass using scales. Record the mass in grams or kilograms. Then you fill a displacement can to just below the spout. You'll notice some of the water will spill out of the spout. That's fine. Get rid of that water. Once the displacement can has been set on a table and settled, you place a measuring cylinder under the spout and you gently lower the object that you want to find the density of, gently lower it into the displacement can. What's going to happen is the water level will rise, and as it rises, the water will displace and fall out of the spout into the measuring cylinder. The volume of water that falls into the measuring cylinder is the volume of the object. Find density by mass divided by volume. And a liquid, well, in this case, you'd place an empty beaker or an empty measuring cylinder and then on some scales, and then you'd zero the scales. So you tear the scales. What that does is it almost ignores the fact that there's a beaker there. Then, once the scales read 0 with the beaker on it, you fill the beaker with a known volume of liquid. Because you've got the volume of the liquid, that's your volume. And as you're pouring in the volume of the liquid into the beaker, what the mass on the scales is actually showing the mass of the liquid. So density equals mass divided by volume. Please correct any mistakes you got there, or add any more information to yours if you'd like to do so. That's always helpful. And we'll move on to the next set. Internal energy. So this one was a simple one in the terms of you didn't need to write lots out, but it was still a bit of thinking in this one. So for internal energy, let's go through the answers. Internal energy of a system is the total energy of its particles. Remember, internal energy is all about the particles. It's the internal, inside of an object. So it's the total energy of the particles in the kinetic and the potential energy stores. Okay, so internal energy is kinetic energy of particles plus potential energy of particles. When a system is heated and the temperature rises, internal energy is increasing because the kinetic energy of the particles is increasing. They're moving faster. That happens when temperature is rising. They're moving faster. So energy is going into the kinetic store of the particles. When a system is heated and the object changes state, so the temperature is no longer rising, but the object changes state, at that point, internal energy is rising because the potential energy of the particles increases. We're breaking bonds, so bonds are broken. The particles are moving further apart from each other. So the energy is not going into making them move faster, it's going into making them move further apart. It's changing state. States of matter can change. So a solid going to a liquid, for example, ice cube out on the table is melting. Liquid to a gas, for example, water in a kettle, is boiling. Solid to a gas, we rarely see this, but sometimes solids can immediately turn to a gas, bypassing the liquid stage. That's called sublimation. On the opposite side, when we're cooling, we can cool a gas back down to a liquid. For example, in a shower, the condensation hitting a cold window turns the steam to droplets of water. That's condensation. Continue to cool it down. The liquid going to solid is freezing. For example, water in an ice cube tray, you put it in the freezer, it freezes. And again, you can get a state where you can get state change, where a gas goes straight to a solid. That's deposition. Again, it's quite rare. Changing state is a physical reaction. It's not a chemical reaction. And how can you tell? Because in chemical reactions, new chemicals are formed. But in a physical state change, no new chemicals are formed. So if you think about an ice cube in a solid state going to an ice cube which is melting, you're not making any new chemicals. It's still water. The water is just changing state, so it's a physical state change, not a chemical one. When state changes, the total mass is the same before and after. So a kilo of ice will melt to a kilo of water. Okay, so mass stays the same, conservation of mass. Please add any information you need to or correct any mistakes before we move on, and give yourself a score on here as well, please. So for latent heat, we're going to split the answers over 2 slides because there's quite a bit on this one. So this is the temperature graph for a substance being heated up. You'll notice that it starts at a cold temperature and it gets hotter. So what you'll notice is there are steps in this. You don't just get a straight line going up, or you don't get a curve going upwards. It's a stepped process when things are heating up. The first stage is, please bear with me for a second, I've seen a mistake here. Okay, this is the correct version now. So the solid at the bottom is heating up. As it heats up, it begins to melt. The flat line shows it's melting. At the flat line, you have a mixture of a solid and a liquid. At the end of the flat line, you've turned all of the solid to a liquid. The liquid begins to heat up. You then get another flat line, at which stage liquid is turning to gas, so you've got a mixture of liquid and gas. At the end of that long flat line, you've turned all of the liquid to gas, and the gas then continues to heat up. This is how your temperature graph should look. Please add any information or correct any mistakes. So this is the same graph, but now it's cooling down, so it's going downwards. You'll notice that we start with the gas because it's very hot starting temperature on the y-axis. The gas is cooling down, so its temperature is decreasing. It then begins to change state. It's condensing. It's going back to a liquid again. The liquid is beginning to cool down. Its temperature is decreasing. As the liquid cools, it begins to freeze. In this case, the liquid has a very high freezing point, melting point. So, not very high, it's relatively high compared to water. The freezing point at which the liquid turns to a solid, so you've got a mixture of liquid and solid. At the end of that, the solid, so the object is now turned to a full solid and is beginning to cool down. What's happening during the flat parts? Well, we've got state changes. You can see condensation, freezing, melting, boiling. They're all state changes on flat parts of the graph. The longest flat part is because we're getting a state change from liquid to gas when we're heating. So what's happening there is you need to put energy into completely breaking the bonds. So a liquid going to a gas, if you go right to the beginning, you can see there that all of the particle intermolecular forces are broken. So in this case, you're breaking those intermolecular forces and we're getting a complete state change that requires a lot of energy. Specific latent heat is the amount of energy needed to change the state of 1 kilo of something without changing its temperature. It's a state change. Latent heat of fusion is the amount of energy to melt a kilo, and vaporization is the amount of energy to boil a kilo. Equation: energy is mass times specific latent heat. Bear in mind, energy has the unit joules always. Mass is always in kilograms. Specific latent heat is joules per kilogram. This equation works for both specific latent heat of fusion and specific latent heat of vaporization. It's the same equation. Gases move at a random speed in random directions. When gaseous particles collide with the container surface, they exert a force at right angles. The pressure is the total force over the total area. Unit of force is pascals. Unit of pressure, is pascals. When temperature increases, particles gain energy, so they collide with the container more often and more force. Volume decreases, there's less space, so they collide with the particles more often. Pressure times volume is constant. If you increase pressure, you decrease the volume by the same proportion. And work done is the last one there. Hi guys.